We've seen that the Schrödinger equation for the harmonic oscillator yields a fairly simple formula for the energy levels of the harmonic oscillator, and that's drawn up here in the slot that we would ordinarily put the energy as part of the Schrödinger equation. The rest of this is the Hamiltonian operating on the harmonic oscillator eigenfunctions. Now, what we want to talk about here are how one would find those eigenfunctions. Usually you would find it at the same time as solving for the energy levels, but I'll assume that we know those energy levels. So really what we're doing is we're solving an equation like this for different values of n. Remember, n can be 0, 1, 2, and any integer moving up. So I've labeled the different eigenstates, or the eigenfunctions, using a subscript n for each of them, which means that we would need to find, whichever eigenstates we wanted to find, we would need to find that function for each different value of n. Now I'm going to say there's two common approaches. I won't say they're the only approaches, but they are two common approaches to solving for these eigenstates. The first, and I'm going to mention this first because I think it's the easier one, but it still involves a little bit of sophisticated mathematics. One can do some algebra using operators, and this operator algebra can ultimately lead to a first-order differential equation and that first-order differential equation would enable you to find the lowest eigenfunction. So I'll call that psi 0. Okay, so that's one way you could do it. And then once you have found psi 0, you would then use operators on psi 0 to generate higher eigenfunctions. I'll say higher n eigenfunctions. All right, as I said, a first-order differential equation is certainly much more solvable, much more accessible than a second-order differential equation, but it does require a little bit of sophistication with operator algebra, and I'm not feeling that that's something necessary for you at this stage of your education, but something I hope that you'll file away and look into. The other one is to basically solve the second-order differential equation that the Schrödinger equation represents. Now, the way one might do this is there's lots of different techniques, but one way would be to note that there's asymptotic behavior. So, what do I mean by asymptotic behavior? As x gets very large, it turns out this part of the Schrödinger equation gets very large relative to this part. So the asymptotic behavior basically says that you can look at how the wave functions must behave as x goes to infinity. And I'll say x goes to plus or minus infinity because it's going to be the same in either direction. And what one finds in this case is that, in fact, the asymptotic behavior of these wave functions is that they go as e to the minus a times x squared. So they go as a square exponential or a Gaussian type function in those limits. All right, once one has that asymptotic behavior, one can then use that to simplify the differential equation, the Schrödinger equation, and use a power series to approximate the various solutions. So we're using a power series to express the solutions. So they would all be expressed something like psi sub n is equal to the sum over all the various possible n's e to the minus a x squared. So we've used the asymptotic part out here to attach it to a series solution, and then we can solve for these various coefficients for the series that represent the various eigenfunctions of the harmonic oscillator. And it turns out that this will enable you to develop recursion relations for those coefficients. I know this sounds like a lot of fun, but I'm going to deprive you of the fun of going through that exercise. However, it's something, if you're curious, you can easily find this particular solution in a lot of physical chemistry textbooks and quantum mechanics books. All right, what I want to do is basically cut to the end and basically ruin the surprise and tell you what the result is. All right, so basically what we find are the eigenfunctions of the harmonic oscillator are as follows. The lowest eigenfunction, which I've already denoted here, psi 0 of x, is actually given as the following function. I'm going to write it mu omega over pi h bar raised to the 1/4 power. Now this is a normalization constant. I hope you recognize that anytime I put a crazy looking number like this in front of a function of x, that I'm talking about a normalization constant. And it is going to be an e to the minus mu omega x squared over 2h bar. So that constant a is actually a crazy series of constants that go up here. So this is the ground state of the harmonic oscillator. And you'll notice that the functional dependence here is essentially a Gaussian function, if you're familiar with Gaussians, I guess. All right, so what about the higher eigenfunctions? Well, I can write in general the solution for the nth eigenfunction as follows. And again, I'm going to start with a bunch of stuff that really amounts to a normalization constant. 2 to the n times n factorial under a square root sign and in the denominator, and again times mu omega over pi h bar, all raised to the 1/4 power. All right, then these are multiplied by a series of polynomials. And these polynomials are denoted h sub n because there's a different one for each integer value of n. The argument of these polynomials is x, not just x, but x multiplied by this weighting factor, square root of mu omega over h bar. And I'll talk about that in just a moment. And then we have again our exponential term that looks like this. All right, so these things here are, as I mentioned, they're polynomials. They have a special name. They're called Hermite Polynomials, named after the same French mathematician that talked about and characterized Hermitian properties. Okay, so these Hermite polynomials have a variety of ways that they can be discovered. There's a particular differential equation that the solutions of that differential equation are the Hermite polynomials. In fact, you'll find that a lot of the things that are named in mathematics are named after the mathematicians who discovered the solution for a particular differential equation, for example. Okay, let me give you an idea of what some of these Hermite polynomials look like. Okay, now I'm going to write these as functions of x, but you will note that in the harmonic oscillator eigenfunctions, they're actually a function of x times that weighting factor. All right, so the very first Hermite polynomial, h0 of x, is just 1. Okay, well, it's not a polynomial at all, it's just 1. The second Hermite polynomial is 2x. The third Hermite polynomial is 4x squared minus 2. Now you notice we're going up one. This was a 0th order polynomial. This is a first order polynomial. This is a second order polynomial. Unsurprisingly, h3 is a third order polynomial, and so forth. All right, these can be generated, if you will, from a recursion relation, and that recursion relation looks as follows. If I want to have the n+1th Hermite polynomial, I need to have the nth polynomial, which I'll multiply by 2x, and I'll need to have the n-1th polynomial, which I'll multiply by 2n. All right, so how does this work? Well, for example, if I wanted to find out what h of 4 is, that would be 2x times h of 3 minus 2n. In this case, n is what? Well, 4 was n plus 1, so n must be 3. So I'll go ahead and put that here. 2 times 3 times h times the second polynomial, which is 4x squared minus 2. So the third polynomial was 8x squared minus 16, 8x cubed, sorry, minus 16x. So when I figure all this out, I'm going to multiply this by 2x. I'll get 16x to the fourth. 2x times 16x is minus 32x squared. Minus 6 times this, minus 6 times 4, 24x squared. And then it's a minus, so plus 12. So I'll end up, all in all, with an expression that's 16x to the fourth minus 56x squared plus 12. And that would be my H4 polynomial, Hermite polynomial in this series. All right, we'll see more about these Hermite polynomials and we'll see what they look like. But they're in effect what gives the harmonic oscillator its oscillatory behavior, because the Gaussian part of these eigenfunctions, and I'll go back to the slide that shows that, the Gaussian part here doesn't have any oscillation at all. It's just a curve that comes up like this, very smooth curve. So this is where the oscillation in the eigenfunctions comes from.